Okay, as we're getting started here, we're going to be looking today at Module 3, which is going to be rolling contact bearings or ball bearings, as you probably have heard them referred to. So if we look at learning plan for Module 3, you're going to notice that we're going to be focusing for this module in Chapter 14, and that's going to be the pages that we see here. It's not the entire chapter. Again, we're going to kind of get started on where the foundation of bearings is, which is going to be radial ball bearings. And then there are extra subjects in there. If you wanted to explore those, or if at a later date, when you're out in the work world, you can always go back in. But the principles and the methods are going to be the same. I do have a PowerPoint presentation out here that we'll be referencing in a little bit. And then what I'm going to do this time is I do have copies of a vendor catalog. The last time we were together, when we looked at the belts, as you can imagine, I mean, it's nice that you don't have to keep the catalogs, on a desk or has to take up space or anything like that. But when you have 300-page catalogs that you're trying to get through on a computer screen, it isn't always ideal. So, so what I have here are targeted pages from a vendor's catalog for sizing and picking out bearings. And I think it'll be a little bit easier to kind of work through. It's not that I don't want to give you the whole experience, but I don't want that to enter into the time. You know what I mean? Because it can get kind of frustrating when you can't find what you need. So we're gonna see how this approach goes. So these are targeted pages that we're going to be looking at. Then you'll notice that we're going to be doing 3 example problems out of the book. 2 of them are going to be manual calculations, the first 2, and then the last one is going to be exploring the Excel spreadsheet that we have to help us out. And then you'll notice that we have the Excel spreadsheet down here below. So if you wanted to go ahead and download that, feel free to do that. And then we'll be referencing the items above. I am going to open up the PowerPoint, the PDF of the PowerPoint. And we are going to get started here. I'm going to zoom out just a little bit to get a little bit more in here. So again, chapter 14 in our book, I've got my book opened up to this. And in the beginning, there's a section on the big picture, okay? Big picture. And so I want you to just take, I'm going to give you, I don't know, it's from one side to there. I'm going to give you 2 minutes to kind of read through that and kind of try to pick out the following information. First of all, what is the purpose of a bearing? And you might already have an idea about it, right? I believe quite certain that you do, but there is, a problem. There's a statement in there that talks about the purpose. Then I also want you to, see if you can find what are the 3 components that make up a typical rolling contact bearing. What is the coefficient of a typical bearing, coefficient of friction? And then identify 3 places that rolling contact bearings are used. And it doesn't even have to be out of that section. It can be just things that you are aware of. So I'm going to give you 2 minutes. So at about 12:10, we'll kind of revisit these. Okay. So starting on this big picture starts on page 563. I'll go underneath my catalog here. All right. And then it goes to the next page as well. Goes to the next page, so put it on the other side too. And I'm going to open up the chat book or the chat so that you guys can put in there. Hi, Evan. We're on chapter 14, right at the beginning here. We're looking at the big picture. So if you have your book, page 563 is where we're starting. You're welcome. All right, it kind of looks like many are looking up and they're kind of done. So, so let's talk about the first question first. What's the purpose of a bearing? Right? What's the purpose of a bearing? Anyone? To do what? Reduce rolling resistance, right? When we have relative motion of one thing to the other where they're spinning in relationship to each other, to reduce that. Yes, absolutely. The resistance too. Yeah. What else? What else is the purpose of a bearing? It can be supportive, right? So what's a typical place that we see bearings used as supports? Right. Yeah. Wheel bearings on a car. Where else? Shafts, crankshafts in an engine, any type of a shaft. Usually a shaft is going to spin, right? Most often doesn't have to, but then we need supports on, you know, different locations, and then having a bearing there to allow that to freely move relative to the whatever the element is with minimal friction or least resistance is really important. Good. Any other thoughts about purpose? I had it highlighted on my page. So then I was like, oh, I can't give him the answer. You'll notice the very first sentence in that section, it says here that the purpose of a bearing is to support a load while permitting relative motion between two elements. And like Jesse pointed out, with minimal resistance most often, right? With minimal resistance. Awesome. Awesome. Okay, let's look at our next one. So what are the three components, typical components? Now there might be more than that, but kind of like, you know, what are the typical three components that make up a roller bearing or a rolling contact bearing? Yeah, so there's going to be an inner race and outer race, the cage, and then also the ball bearings, right? So on page, they do have a nice illustration here and even a cutaway on the following page, page 564. Here are those elements. So we've got the balls, the cage that keeps them in there, and then the inner and the outer race is kind of considered, one, if you would. Okay, good. What's my next question? I gotta go back. What is a typical coefficient of friction that we would expect out of these types of bearing, rolling contact bearings? Coefficient of friction. Yes, so on that same page, I think it's right about here, right? The coefficient of friction is very low, all right? Coefficient of friction is going to be anywhere from 0 all the way up to just 1. Okay, so these are very, very small numbers. When we think about our tires on the road, we want to be as close to 1 as possible. Okay, we want to stay on the road, especially in winter. We want a good tread. But as that wears away, obviously the coefficient of friction gets less. When we have elements like this, where we want to minimize that resistance, now we want to really kind of pull that down as low as possible. Okay, so that we can get free movement. Good, 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 good. Our next one is identify 3 places rolling contact bearings are used. So we already heard about wheel bearings on cars, crankshaft bearings. Where else do we see bearings? Rollers on an assembly line. Yep, absolutely. Gearboxes. Yep, on the shafts, right? That are going to be then supporting the gears and stuff. How about our virtual people? Put in the chat box, or you can say it for audibly. We should be able to hear you. Where else do we see bearings? Drawer slides, absolutely. Yeah. Yeah. Motors. Different places, especially with those shafts, things that have to rotate. Exactly. Good. Any others that anybody wants to add? Okay. All right. So that's kind of a nice little entry, if you would, to what we're going to be talking about today. So we're going to kind of get you in the mood, if you would. So objectives of this chapter. So first and foremost, we're going to identify different types of rolling contact bearings. We're going to select a bearing based on load and life expectancies. So that's what we're going to use our vendor catalogs for. And then we're going to specify the mounting details used or using those manufacturers' recommendations. It's one thing to be able to say, this is the bearing that we're going to be using, but then as a designer, as an engineer, you've got to incorporate it into your design. And so you've got to be able to then take that next step and find out, okay, what are the appropriate tolerances that we need to use in order to meet the loads and the life that I'm expecting. So going to kind of catch us up here in our chapter. So different types of bearing loads. So when we are talking bearings, there are two main types of loads that we're going to be using to size and to pick out the appropriate type. And the first one is called a radial load. So a radial load is going to be directed perpendicular to the shaft, and then a thrust load is going to be directed along the shaft. So I wanted to kind of go underneath and just draw a brief little diagram of a shaft and where we would have a bearing and what this, these directions of these radial and thrust loads mean. So I'm going to go on the side here. I'm going to draw a bearing, or I'm going to draw a shaft first. I'm going to put a bearing on it. Okay. This is going to be a shoulder. And then I would have my bearing, something, maybe it would be a little bit taller. My bearing is going to be in here, and it's going to be on the shaft. A little bit taller on the bottom than it is on the top. That's okay. And then typically we just show this kind of as a schematic. This would be where my rollers would be. My inner race would be in contact with the shaft. My outer race would be out here, probably pressed into a housing. Okay. And then it would be free to move by those ball bearings that are on the inside. So as we look here, and we talk about radial and thrust loads, a radial load, as I said in the description there, which I don't think is a great description without seeing a picture, a radial load is going to be looking at this point, and the load that it's going to be supporting is going to be perpendicular to the axis or to that shaft. Okay, that's a radial load. So back in statics, you guys would have looked at beams, and you would have found the reactions at the supports. And if your reaction at the support would have been perpendicular to the axis of the beam, if you would, that would have been considered a radial type load, or a radial orientation of a load. So that's the first type of load that we're interested in supporting on a bearing. The other type of load is what we refer to as a thrust load, or sometimes we can think of it as a side load. And that's going to be a load that's going to come in from the side. Okay, so this is going to be a thrust load. All right, or a side load, as I said earlier. Now, at times in statics, you would have had forces that maybe came in at an angle on something. And when you broke it into its X and Y components, that Y component would be a radial, and that X component would have been a thrust, or what may be referred to as a side load. Okay, those are interchangeable. So those are the two types of loads that we are, if you're not really concerned with, but we want to identify, is there a thrust load? Is there a radial load? And what their magnitudes would be? Because then it starts to give us the direction of what type of bearing are we going to be interested in. Okay, so radial, perpendicular to the axis. Thrust or side load is going to be along the axis. Okay. Now, the other issue that we are concerned about with bearings is the angular deviation or the misalignment. When we are using bearings, especially in that classic example of supporting something that's going to be rotating like a shaft, we need to make sure that that shaft, when it's mounted, is going to have a nice straight center line, okay? And that's going to have to align from one bearing to the other. You can imagine that as we get further and further, apart on these bearing supports, it's going to be harder and harder to align, right? So misalignment, we have to take that into account, because certain bearings can take a little misalignment, certain bearings can take a lot, and certain bearings can take almost none. All right. And if we have misalignment and they're not intended to misalign, we are not going to get the life out of them that we were anticipating. Okay. Because they're not lined up properly. Okay. So that's going to be something else that as you start to pick them out, you're going to have to be aware of how you incorporate them into your design to ensure that the appropriate alignment is held. Okay. Now in our machine design elements, we aren't going to be going quite that far, because we're not going to be incorporating them into a design until we do our gearbox project. So right now, that part of it, we're not going to worry so much about. Okay. We're going to be basing our decision for bearings on the load and the life that we want to get out of it. And then after that, when we incorporate in our design, we need to look to the manufacturer's data to be sure that we're in alignment with that. Okay. So when we do our gearbox, we'll be looking at that. Types of rolling contact bearings. This is going to be our next section. So I'm going to go back underneath here because we've got a bunch of pictures to look at. So the first one that we come upon here is going to be the single row deep groove ball bearing. This is the most common, considered what we call a radial bearing. And it's the one that's pictured where we just were looking on 14.1. You'll notice the inner and the outer race, the retainer for those bearings, and then the rolling elements that we see in there as well. This type of a bearing is designed to take both radial and thrust loads, but the thrust loads aren't very high. It's more intended for a radial load, and they are a lot of times referred to as radial bearings, okay? But it can take some. And really for the fact that sometimes on those misalignments, or if they end up coming up, they can take a little bit of thrust load. And then the other thing about these, you can increase that load carrying capability in a couple different ways. You can increase the size and the number of the balls that are on the inside, and those will then help you to increase that load carrying capability. So as you can imagine, the larger the bearing, the higher the load that it can actually take. Okay, so let's take a peek underneath again at the single row deep groove ball bearings. Now I happen to have some bearings here. All right. And if you're in the room, you get you get to kind of, see these as well. But I think the pictures are pretty good and pretty self-explanatory. So here we have a bearing. You can see the inner race, the outer race. Okay. The inner race moves real freely, hardly any friction there. You can feel it a little bit, but it's nice and smooth. And then those balls are inside of, and you can see the little cage. I know probably underneath the camera, not so much, but they're there. Okay. So I'm going to pass this around in the room, but you kind of get the idea there. I don't know how, maybe it's longer ago than I thought, but remember fidget spinners? Those are ball bearings, right? Those are ball bearings. So if you had a fidget spinner, you've played around with these, and they can be kind of like, I'm not going to say it's not addicting, but it's like you want to kind of, play with it. All right, let's get back. The next one is a double row deep groove ball bearing. And so here, you're going to really just notice that it looks very similar, except obviously we've got 2 rows. So as we look at this type of a bearing, what do you think would be different on a bearing like this than the single row? How do you think a double to a single changes, or a single to a double? What was that? Yeah, you could take up some more side loading. What other type of loading would increase? Radial. Yeah. Now we're distributing that load over 2 rows of bearings, right? What's going to probably be harder to do with this type of a bearing? Aligning them across. Now you've got a wider stance, if you would, on that bearing. And because you've got that, then you're not going to be able to misalign them quite as much. So you're going to have to be a little bit more careful. Not that it's a big deal, but it is something that's going to be, different from the single row. So let's go back over here. 2 rows increase requires higher precision on alignment. Awesome. Okay. Angular contact bearing. Angular contact bearings are going to be on one side. The race is higher than the other. And this is going to deliberately accommodate higher thrust loads, or those side loads. Okay. So they can take both radial, but just the intentional arrangement there for the ability to take a side load. And those are here. So you can kind of see that one side and the other of the of that inner and outer race kind of capture that ball, so that when it's pushed on one side or the other, now it can take that thrust load a little bit more, a little higher thrust load. Okay. So that's an angular contact. Looks very similar. Probably even if you would be looking at it on a table, it wouldn't look any different than a ball bearing, like a regular ball bearing. But the way that the races are, the inner and the outer races are, you will have that ability to have a higher thrust load. The next one is cylindrical roller bearings, okay? Cylindrical roller bearings. These are going to employ actual cylindrical rollers rather than having the balls. Now, in theory, the balls are going to give you what they say is point contact, but when you get compression there and you actually, put a load on there, it squishes out a little bit. There's some deformation and you do get a small area of contact. Now, on rollers, on the other hand, you get like a line of contact on that roller. So just like we did for gears, where the wider you would have a face width, you would be distributing a load over a line rather than like a smaller point or a real small area. So roller bearings give us very high radial loads, okay? They cannot withstand any thrust load though, unfortunately. So they're all built for radial loads. So this is going to be, so again, you see that inner, that outer race, you see I have a means of keeping those rollers in there, but now we've actually got line contact as opposed to just kind of that point or that small area contact. The next one is a needle bearing. A needle bearing is a version of the roller bearing. And the only difference between a needle bearing and a roller bearing is that the needle bearing has much smaller diameter on the, I thought I had one here. Yes, I don't. They're just smaller on that diameter. So let's go over here. The needle bearings are up on the next page, okay? So you'll notice that again, you've got rollers, but they're just a lot smaller. So in this case, what it does for us is it allows for us to have these in a smaller area, okay? So it's actually going to accommodate, let's say I can't have this big roller bearing because roller bearings tend to be kind of large. And I don't have that difference. I might need a lower profile. So here you're going to have a bigger thickness. Here it's going to be much lower, okay? So you can fit them in. But kind of the nature of what you see here is that we get now a wider stance again, and alignment becomes really critical, in order for these to roll properly. You see them a lot in cam followers, okay? So that's another application. Poor thrust load capabilities again. Spherical roller bearings. Spherical roller bearings, they're going to be similar in load carrying capabilities as a roller bearing, but these are more misalignment tolerant. So if we go back underneath here, these are going to be our spherical roller bearings, and notice that they tilt them on either side. So it also offers us the ability to, taper roller bearings on this side. Taper roller bearings can also take a side load. So these are more of a cone cylinder shaped as opposed to just a straight cylinder. And then we have spherical roller bearings here, and you'll notice that we tilt those cylindrical rollers on either end, which helps with misalignment. Okay, so they can take a little bit more misalignment than the others. Okay, that's the next one. Oh, taper and then spherical. Yep. Thrust bearings. Thrust bearings. These types of bearings are intended to only take a thrust load, not to take any radial load at all. So these are actually, they look a little bit different, and you've probably seen these. And I have the inner of a needle bearing, or I'm sorry, a thrust bearing. And so I'll send this around, but you'll notice that there's a top plate, a bottom plate, and then in the middle is where they actually sit. And so you get relative motion this way. I like to think of it in terms of I don't know if everybody understands what a lazy Susan is. Okay, that has like, that same type of action. So these are intentional thrust, or they take only thrust loads, no radial loads at all. You wouldn't tip these on their end and actually, put a radial load on there. So I'm going to show this to you guys underneath. So this is kind of that inner. So you would not tip it at its end and put a shaft through here and have any radial load. This only would, sit and and rotate relative like this. Okay. So I'll send this one around. The next ones that we have here are called mounted bearings, and these are used a lot in like open frame machinery. So packaging equipment where you're going to have shafts that are going to be held across across framework. These are going to be where we're going to see these types of bearings. I used to incorporate them a lot. I worked at a company where we did high-speed wrapping equipment, and so we used pillow block bearings and flange type bearings all the time. So let's take a peek underneath here. So on the bottom here, we've got, this is called a pillow block bearing. And so what's nice about a pillow block bearing is it kind of encloses itself, and then you can take these holes and you can just attach them down to, for instance, a frame. And now you've got everything enclosed on the inside, and you can just put your shaft in, tighten it down, and away you go. It also allows for adjustment at assembly. So when you're, actually putting it in place, you can line them up and you can kind of move this back and forth as needed. When you're in a situation, like I talked about high-speed wrapping, you got to have the alignments on really nicely. So you need to have this amount of freedom, especially when you have, frames that are 6, 7, 8 feet wide. Okay. The other type is going to be a flange bearing. So they work very similarly, except now they're going to support in just a little bit different directions. So this would actually mount up onto, for instance, a frame, and then your shaft would go through. You would accommodate that through the frame as well. And then the last ones are take-ups. These are really nice and flexible because a lot of times, especially in the industry I was in with packaging equipment, you want to be able to utilize that machine for maybe different widths of product. And so if I have toilet paper that's going through, maybe it's only 2 wide, but then my next package is going to be 4 wide, I've got to be able to adjust that. And so having it on an adjustable, what we call take-ups, you can mount those to the frame, and then you can actually, go through the setup and change it over really easily. So those are nice as well. Bearing materials, okay? Bearing materials. Bearings have to have a very high ability to resist stress because the contact that they have is going to be on very small areas. And we need it to be small because we want to minimize the amount of friction that we're going to encounter, right? We want to keep that coefficient of friction low, so we don't want to have a lot of surface contact. So so that means that the materials that we pick then, because of those loads being concentrated in such small areas, they have to be able to take a high stress. So 300,000 PSI, that's like no joke, okay? So so you're going to have very hard, high strength steels as going to be those balls on the inside and those inner and outer races. You'll also see ceramics be used for balls, rollers, races to distribute those loads over. And a typical material would be an SAE 52-100 steel. So if we look at table 14.2 in your book, which is on page 570, here are, some options that we would have for different types of materials. So the different materials are kind of coming down here. Here's that bearing steel, the 52-100. Gives you the density, modulus of elasticities. I mean, we're 30,000, that's KSI. So add another 3 zeros there. And that's a lot of resistance. That's a lot of stress. Okay. Hardness levels, as well as, their max temperature. Now, as you look here, the max temperature, 570 degrees. That's pretty hot because, as you know, if bearings, especially if they're failing and they don't have the lubrication that they're supposed to, all of a sudden they start really heating up, and that's when you can start hearing them, right? If we go to the right here we've got, temperatures that they can take, especially the ceramics. They're crazy. Here's a carbide, 3,100. Okay. So you can get pretty fancy with the materials. But as you can imagine, right, as these capabilities go up, what else goes up? Probably the cost, probably the price. Exactly. So so that's where, as the designer, you're going to kind of, find that reasonable medium, okay, where you should land. We all want our bearings to last forever, but you're also going to come at a cost, right? So yeah. So that's there. Load versus life relationship on bearings. So the lighter the load, the longer the life. So we're going to find that in the catalogs, there's going to be a rating on our bearings. And it's gonna be a life rating that we're expecting, and it's gonna give a load to accomplish that life. But let's say we don't have a load that's gonna be that high. Well, that means then that we get the advantage of now we're going to get more cycles out of it, which is good. So on page 571, I'm going to kind of erase my marks here. There's the equation 14.1 that gives us the relationship for that bearing load to bearing life. So as we look at the L's here, the L's are the amount of life that we're expecting out of these in revolutions, okay, or cycles, if you would. So how many times are those going to go around? And then the P's are going to be the loads. As you can see here, we would line up what is the load and the expected life with the L and the P ones, and then what is the load and the expected life with the P or with the L2s or the L2 and that P2. So for instance, my L1s will probably be out of the catalog. Like, what are the numbers out of the catalog that I'm going to get? Meaning, what is the load and what is the expected life? And we'll talk about that in a little bit. And then if we have a different load that we're putting on it, okay, then what is the life that we would get out of it? That would be our twos here. So this would be our life that our load that we would be putting on it. So what is the life that I would actually get out of it with this ratio? Now, it's not a perfectly linear ratio. Notice that you have this K value that you have to put up there. And you'll notice that for a regular ball bearing, that K value is 3. If it's a roller bearing, it's 3.333 and so on. Okay. So we'll be using this in just a little bit. Now, I can also tell you too that the opposite can happen as well. So if we don't get to that load carrying capability, we can put more load on that bearing, but we're not going to get the life out of it. Okay, so it goes both ways. So the higher the load, the lower the life. The lighter the load, the higher the life. So we'll play with that when we do our examples. Now, manufacturer's data. Manufacturers, if they are bearing manufacturers, they kind of have a standard that they, need to live by, if you would. So there are standard classes of bearings. And if we look at the bottom of page 571, we're going to see this illustration. Zoom out just a bit. Starting on the left-hand side, assuming center line here is the same for all of them, and they all have the same bore, okay? On the left-hand side here, this is considered an extremely light category to an extra light, light, medium, and heavy. And you can just see that for that same size bore, so this is just half of it. So this is one side, here's our center line, the other side would be down here. For that same size bore on each one of these bearings, notice how they get bigger, okay? So as a manufacturer, you line up with one of those categories, all right? Or not one of them, you can make multiple categories, but you would make it in that standard category. And then standard sizes as well as standard load carrying capabilities. So if you're a Fafner bearing or a Torrington bearing or an anything else bearing, you're going to have, something, for instance, in any one of these, is you're going to call it a medium bearing. That means that you're meeting the specifications, load, and also dimensions for that bearing. Many manufacturers will then have their own series of bearings that might, make them or differentiate them. But if they're claiming to be an extra light, a medium, and they adhere to this series number, then they're making those to those standards. Okay. Which then, to the advantage of the designer, now you have a store to pick from, if you would. So if somebody says that they're an extra light 100 series, you can pick from anybody who has an extra light 100 series. And if you're trying to do, for instance, a cost reduction on a product line, now you can say, okay, what's your price and what's your price and what's your price? And you should be getting the very same bearing from each one of those places. Okay. So just know that there is a standard here in the bearing world, which means then that as you look a little bit further, oopsie, wrong way. As we look a little bit further in our book, we turn actually to the next page. Now we have a set of tables here for single row deep groove bearings that are in these series. And so you'll notice the part number is going down the side. You're going to see the bores. outside, inside diameter, those are all standard sizes. Okay, that's why they can put those here. But again, Fafner is going to have some, Torrington, NSK is going to have their own, and you can then pick, right? When you're picking from catalogs like McMaster Carr is getting them from these bearing catalogs, okay, or these bearing vendors. McMaster Carr does not, I don't think they make anything. I think they're just a distributor. So you can find a number of different products there, but typically they're kind of that middleman. They're going to be a little bit more expensive, you know, than what getting it from the actual vendor is going to be, which makes sense, right? They're kind of that, they're the middleman. So, but they're also a nice source where you can get something like quick, and they have like almost everything, right? So, so depending on what your needs are, if it's something you're going to buy over the long term, you probably want to go straight to the vendor. If it's something you just need one off, McMaster Carr is a place that you can go for like everything. But anyway, they'll have bearings like this too. And as we go across, we're going to be looking at our manufacturers' data, and we're going to see many of these very same things. Okay, so so standards in the industry. Bearing selection charts. So the two things that we're going to calculate to give us our start and to determine which bearing is going to, you know, fit our needs is going to be number one, the basic static load rating, and number two, the basic dynamic load rating. So basic static load rating is the load that a bearing can withstand without permanent deformation. So this is the force that you're going to calculate based on the reactions at those supports. So just like when you were doing the reactions on beams at their supports, we can simulate a shaft, and its supports are going to be at the bearings. And this is going to be the number that we find that we use for that basic static load rating. It's going to be the reaction at the support. Okay, so once we know what that is, we've got that one done. But the other one that's here is the dynamic load rating. So static, dynamic, what do you think the difference is? Static would be not moving. Dynamic is now we're rolling, right? Now we're rolling. So the dynamic, the basic dynamic load rating is going to be the load for which the bearings can be subjected to, and they will achieve a rated life of 1,000,000 cycles or 1,000,000 revolutions 90% of the time. Okay, so you'll notice that it says L10 life. Okay, so whatever the dynamic load rating is, it's gonna be in the catalog rated right there, and it's gonna mean that 90% of those bearings make 1,000,000 cycles with that load. Okay, with that load. Doesn't sound great, does it? It doesn't sound great, but this is where the lighter the load, the longer the life. The heavier the load, the shorter the life. Okay, so you can go up a size or 2 or 3 on your bearings because you want a longer life out of it. Okay, so so those two forces. Now there is a third variable that works in here, and it's going to come, and it's gonna be something that's gonna feel more applicable when we do shaft design. But the other part of this is when we do our shaft design, we are going to be sizing for minimum shaft diameters. Those minimum shaft diameters say we need this much of shaft material in order to resist those loads. And when we are at our bearing locations or at our supports, we're going to have a minimum shaft diameter that we also have to keep in mind. So we not only have to worry about load, but we also have to worry about the minimum shaft diameter. In this chapter right now, we won't be worrying about shaft diameter, but when we do our gearbox design, you will have had shaft design, and then we're going to be adding that variable at that time, okay? Because we have to fit it into our design, and we have to make sure that the shaft is accounted for as well as the loads, okay? So, but for right now, the two loads, basic static load rating and the dynamic, are going to be what we're going to be using to size. So let's look at example 14.1 and kind of start, you know, crunching some numbers here. So on a page 575, this is going to be where we see this problem. So let's go underneath here. So what I'm going to do, I'm going to kind of go right here. So, so on page 575, example problem 14.1, it says we have a catalog. It lists a basic dynamic load rating of a ball bearing to be 7,050 pounds for a rated life of 1 million revolutions. So again, in the catalog, that number that we see down the dynamic load rating column is going to be based on 1 million cycles. Okay. Or I say cycles, revolutions, you know, that many times around. Okay. What would be the expected, what we call L10 life? They call it L10 life because, and I think it's kind of opposite, even though that number means that 90% are going to make it, 10% won't. And I'm not sure why they call it. I would rather, I think L90 sounds better, but L10 is what they've always called it. So 10% won't make it. So they call it an L10 life on a bearing. What would it be if it would be subject to 3,500? So you'll notice that it's a lot. We have 7,050 as our basic load rating, and it's lining up with, I'm going to get 1 million cycles out of that. But now if I'm going to reduce that to 3,500, what will be my life now? Okay. So let's kind of figure out what variables that we have here and what we're going to be using. So I should actually go back. The equation we're going to be using is going to be on page 571. This is the one that we talked about and identified as the lower the load, the higher the life, or just the opposite. So this is the equation we're going to be looking at. So I'm going to start by writing that first. I'm using pen only because I feel like when I was watching my videos, sometimes the pencil is not the easiest to see. So don't do what I'm doing, do what I'm telling you to do. So make sure that you use pencil. Okay, so my equation is L2 over L1 is equal to, and in parentheses, we're going to put P1 over P2, and then we're going to take it to the K power. Okay. Now that K power, remember, is different numbers depending on if I'm a ball bearing or a roller bearing, and we're using the ball bearing number. So our K is going to be equal to 3. So as we look here, all of our ones are going to be out of the catalog numbers. So for instance, P1 is going to be that dynamic load rating of 7,050 pounds. Okay. Which means that our L1 is going to be 1 million cycles. So we can say 1 times 10 to the 6th, and that's going to be revolutions. I keep saying cycles, revolutions, which is a cycle of a bearing once around. So that means that our L2 then is going to be our unknown, and our P2 is going to be the 3,500 pounds. Okay, so notice how they go together. And then our K is going to be 3 because it's a ball bearing. Okay, so I'm going to just kind of put an asterisk here so that you know this is equation, I think it was 14.1. Yep, 14-1, and this is found on page 569. Just as a reference if you wanted to, you know, find where that was. Okay, so now what we're going to do is we're going to plug our numbers in, and our only number that we don't know is the L2. So it's kind of positioned nicely, right? So so we can rearrange here if we wanted to. So P2 is going to be equal to P1 divided by P2 to the K, and then we're going to multiply by L1, right? That's our algebra. So go ahead and plug your numbers in and see what you get. So I'm going to put mine in here. Remember to put your units in all phases of the problem. I forgot my calculator. I'm gonna have to rely on you guys. That's okay. So get your calculators out. Let me know what you get. Don't forget to take the P1 over P2 to the 3rd power before you multiply by 1 million. And then our pounds cancel out. We're left with revolutions, which makes sense for the life that we're expecting. How many revolutions are we going to get? And even if you're virtual, you can let me know. What did you get for the number for L2? And I know the answer is in the book, and that's great, but I want to make sure that you can get the number on your calculator, using your process. 8.17. Yep, look at that. That looks good. 8.17 times 10 to the 6th. There you go. 8.17. See, this is why I am not a big fan of the pen. Times 10 to the 6th. And that's going to be revolutions, right? If you can read my number here. Ugh. Stand it. Revolutions, because revolutions was on my life for L1 and it wasn't canceled out. And now I'm going to do an L2. So I'm expecting that very same thing. So notice what happens. So, I doubled, or I halved my load. And how many times greater did my life come out to be? Yeah, a lot, eight times more, right? Yeah. So that relationship is not linear. It's considerably more. Okay. So, questions on that? Talk about design life. Design life in terms of hours. Many pieces of equipment, instead of having, how many revolutions something is, or how many miles something goes, many times they're rated in hours. So like agriculture tractors, how many hours are on that tractor? Lawnmowers, I think, are hours as well, right? Hours. And so things that are inside of that are running, a lot of times we might want to say, I want to get this many hours out of it. And knowing how fast it's going to be rotating, what its RPMs are going to be, we can then calculate our life in terms of hours as opposed to just revolutions. Okay. So you'll notice that on that same page, a little bit further down, we have some design life calculations here. So to figure out our design life in terms of hours, a lot of times what you want to do is you want to look to the industry. So down here on table 14.4, these are recommended design lives of bearings. Okay. So if we look here, automotive, you want to get anywhere from 1,500 to 5,000 hours out of a bearing. So instead of taking it in terms of how many revolutions, because that would be like a lot, really big number. Now we're looking at how many hours are we expecting to get out of that particular bearing. Okay. If we look at other industries, like here we've got electric motors, we've got industrial blowers, industrial machineries, conveyors, 20 to 30,000 hours we're expecting out of that. Okay. So once you kind of know what industry you're in, or even what the requirements for your particular company might be, your company might say, the industry says 20 to 30, but we want 50,000. Okay. Because we're better and we have a more quality product. We want it to last longer. So that is how you would determine, what those hours would be. Okay. Now, what we're going to do is we're going to look here, our dynamic load rating. You'll notice that this is capital C. When we look in our catalogs, we're going to see that capital C is the variable that we use for our dynamic load rating. So now we're going to be looking at what is the design load, and then LD is going to be the design life, And then you'll notice divided by 1,000,000, and then this is going to be 1 to the K. So this is going to be what, if you would, the P1, the original P1. Now, when we go down here, design life, if we want that in hours, then we're going to convert it using that equation here. So we're going to go from hours, we're going to multiply it by however many RPM there are, so that we can get the revolutions then to put up in this equation, because we're going to need revolutions for that one. So let's do an example here to kind of use these two equations and see how they're related. So example 14.2, this is another one for your practice problems. Example 14.2, we want to compute the required basic dynamic load rating, C, for a ball bearing to carry a radial load of 650 pounds from a shaft rotating at 600 RPMs, okay? It's going to be part of an assembly conveyor in a manufacturing plant, Okay, so right now what we want to do is we want to determine what that life is going to be for that bearing, that design life, based on it being an assembly conveyor in a manufacturing plant. So if we go down here and use this as our guidelines, you're going to notice that this line probably is going to be the one, the 20 to 30,000 hours. So you then would know as a designer, does that seem like a reasonable number? And that is that, you know, what your company or what your product line is using. So for right now, we're going to say yes. And you'll notice that they used 30,000 hours. So we're going to use 30,000 hours in our calculation. So the first thing we're going to calculate here is going to be our design life. So our design life is going to be the number of hours times how fast it's going in RPMs. And then we're going to multiply that times 60 minutes per hour to get rid of the minutes. We'll kind of expand this out to make a little bit more sense. So H, our number of hours, is going to be 30,000 hours. Oopsie. Hours. Okay. And then we're going to multiply it by the revolutions per minute. Now, when we do revolutions per minute, don't write RPM. Our revolutions per minute that it's going to be going is going to be 600 RPMs. So we're going to go 600 and we're going to put revolutions on top and minutes on the bottom. Okay, so you have to write it out like that, because now we're going to multiply it by 60 minutes per hour. Okay. So notice when I multiply across the top, divide by the bottom, my units cancel top to bottom here for minutes and for hours. And I'm left with revolutions. So now this is giving me my number of revolutions that I would expect when I'm going 600 revolutions per minute for 30,000 hours. That's all that this is. It's really, if you would, a conversion. So my LD then is going to be a really big number. What is your number? I could use my phone. I don't like my phone calculator. So 10 point what? 8 times 10 to the 8th. And then what are my units? Revolutions, exactly. So now, I mean, it's nice to put it in the times 10 to the 8th, but let's just go 10 and then 1, 2, 3, 4, 5, 6, 7. Is that 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 1, 2, 3, 1, 2, 3. There you go. That's how many revolutions in 30,000 hours going at 600 RPMs. That's how many revolutions we're going to need out of that bearing. It's crazy town. It's a lot of revolutions. Now that we know what our design life is, now we can calculate what is the dynamic load rating now. Okay, what is our dynamic load rating so that we can achieve that number? Okay, so to do that, now we're going to use the equation right here. Now we're gonna show it in up-down format, like I like to call it. We're not going to do slashes, okay, like they're showing here. So let's write that equation. So this is going to be C is equal to our design life, or I'm sorry, our design load. Sorry, I can't see this. Our design load divided by, oh no, I'm sorry. See, this is why I don't like this. We'll try again. C is equal to our design load times, this is my up down, my design life divided by 1 times 10 to the 6. That's 1 million. Okay. Times 1 over K. So now our design load, we're going to go down here. Our radial load in the problem tells us that it's 650 pounds. So 650 pounds times our design life. That's this one right up here. I'm gonna write it at 10.8 times 10 to the 8th revolutions, right? Divided by, now this is just divided by 1 million. It is 1 million revolutions, yes. So revolutions is going to cancel top bottom. And then the factor up here is just going to be 1/3 because we're a ball bearing. So it's to the 1/3 power, to the cubed root. So now I'm going to say C is equal to, this is 650 pounds. It's LB here, not 6,501. So what do we get for a number? Everybody should be plugging this in. Make sure that you can get the same number as the book. Okay, so you should come up with something right around 6,670 pounds. You have the same number? Be a chance to plug that in. If you're done, did you get 6,670 pounds? Yeah, I see nods. Anybody not get it? If you have to do it in steps, you know, that's totally fine. All right. We'll go back over here. So we did example 2. Now let's talk about bearing selection. All right. So when we have just the radial loads only, and that's going to be what we're going to be focusing on for the exercises that we do next, is first of all, you need to know what your equivalent load is or what your radial load is that's actually going to be on it. So this is the number, like I said earlier in statics, you would have calculated what is the reaction at the support. Okay, that's this number. Then you want to determine you want to know what is that minimum shaft diameter or the minimum diameter that we have at the placement where we're anticipating putting the bearing. In our cases, we're not going to have that for our homework problems right now. But later on, when we revisit bearings in our gearbox design, we will. Okay, that's going to be the shaft design part. Then what you're going to do is you're going to determine what is the type of bearing that is going to make sense for me. Okay, so is it a radial ball bearing? Is it going to be a thrust bearing, a roller bearing, whatever? Okay. Then you're going to compute the dynamic load rating for that bearing. So we're going to use that C equation that we just looked at. You want to select the bearings that would make sense, okay, for the C up here. All right. So what are the bearing, the bearings that would qualify based on the dynamic load rating? And then you also then want to check it based on size, meaning what is the minimum shaft diameter I need? What is the minimum bore I have to have in order to also accommodate the amount of material I need there for the shaft? And then determine your mounting conditions. Now, mounting conditions are going to be what the bearing manufacturer tells us are the appropriate tolerances for the outer race to be pressed in and for the inner race to be pressed on a shaft. Okay. If they are not sized appropriately, 2 things can happen. Number 1, you don't have enough press to keep it from moving. Number 2, you could have too much press that when you compress those bearings, they're not going to get the life that you're expecting out of them because you're now inducing extra deformation that they're not anticipating. Okay. So you have to use manufacturer's data for the mounting conditions, and you will do that for me for your problems because I want to make sure that you're getting that. And then those numbers, those tolerances are going to be what you add into your designs. Okay. So what I'm speaking about there is, I'm going to kind of go underneath our camera and we're going to look at chapter 15. And we're going to be visiting chapter 15 when we do our gearbox design, because this is a chapter that kind of runs through that process. And on page 593, they have an illustration of a gearbox. So the gearbox is the part that we're going to be looking at designing, and we're going to be sizing bearings. Okay. And those bearings are going to be the supports on either side. Kind of zoom in. I know it's not the easiest. Either side of the shaft so that the gear can rotate nicely and freely on the inside. Now, when we do our shaft drawing, okay, I'm going to go over to pages 606 and 607. Here's an example in this chapter of the shaft drawing. Now we're going to have two bearings on this shaft right here and right here. And as I zoom in, this is the dimension for the diameter that shaft has to hold to accommodate the bearing for the size so that we get this life out of the bearing that we're expecting. This is the manufacturers telling us this is the tolerance you have to put on there. If you start having bearings fail early and you say, hey, Fafner, we're having a problem, the first thing they're going to do is say, let me see your drawing. Okay. And if you did not incorporate their tolerances, they're not going to stand behind it. Okay. End of story. So you have to take that, and that's any vendor. And I know we've said this a couple other times as well, but it's really important when you're using vendor information that you are speccing it out the way that they're telling you. You have to put it into your design, even if you think you know better. All right. If there's a chance that there could be a failure that you need to go back to them on, you have to prove that you use their information and that you sized it appropriately. Okay. So we're going to be finding where those are in the catalog pages, for our assignments as well. Okay. That's mounting conditions. So let's look at example 14.3 and walk through this process. Now, bearings, there aren't heavy duty calculations, if you would, but I do have a spreadsheet to help us. And it also is kind of nice to summarize the information as well. So on page 576, you're going to find problem 14.3. Before we go there, I encourage you to download the Excel spreadsheet if you haven't done so already. So I'm going to download it here. I'm going to go to my learning plan, module 3. I think I have it downloaded, but just in case. And then I'm going to pull it up and Excel will open. And we'll kind of just let this sit here, enable editing. You're going to probably want to save your own somewhere so that you have it, and rather than just in your downloads. So I'm going to go back to, and I'll catch myself back up on our slides. Mounted bearing. 1, 2, and we are on 3. There we go. Okay. 2 and 3. All right. I'm going to go underneath. We'll look at the problem statement here so we get all the details. And it says here, this is on page 576. We want to select a single row deep groove ball bearing to carry 650 pounds of pure radial load from a shaft that rotates at 600 RPMs. The design life is 30,000, sound familiar, and the bearing is to be mounted on a shaft with the minimum acceptable diameter to be 1.48. This would be what the minimum shaft diameter is. So this has to be the smallest bore that this can take. So they're adding that information for us. So what we're going to do is we're going to go to our Excel spreadsheet and we're going to input this data. Okay. So I'm going to just increase this a little bit so we can see it. Over. So down the C column, this is our same familiar format. Down the C column, we're going to put first our radial static load. Okay, so that's going to be our 650. And notice on the right-hand side, it's pounds. Then we have rotational speed. What is the RPMs that this shaft is going to be rotating at? 600 RPMs. And then the design life in hours they're giving us is the 30,000. So now it's automatically going to calculate for us what is our L10 life, which is exactly what we got earlier with the manual calculations. What is our dynamic load rating? This one is not rounded to 3 significant digits. And then it says, what is that radial static load rating? Okay. So you'll notice down at the bottom here, we have a design summary. Now you are going to be filling this in. This is not pulling numbers from the top this time. You could for the static and the, well, no, you can't, because this is going to be based on what you choose. So these are going to be fill-ins to finish the problem. Okay. So the first thing that we want to do is we need to find out what bearing is going to work for us. Now, the bearing that they chose is going to be different because they use the catalog or the textbook pages here. We're going to use a catalog pages that I have here on Canvas. So we're going to go back. We're going to go to Module 3, Learning Plans. And what you're going to want to do is just quickly download the 3 catalog pages right here. Okay. And then we're going to reference those. The first one we're going to look at is going to be radial ball bearing Fafner catalog pages. And this is not an entire catalog. This is 6 pages of a section. Okay. And I want to show you, oops, I made it bigger. Oh, shoots. I wanted to kind of scooch it over. What I want to show you are the categories or the columns that we're going to be looking at here. So you'll notice that we have an extra light 9300K series. Okay. And on the right-hand side there, they're giving us the nominal sizes. I'm just going to zoom in a little bit here. And the capital D is going to be the outside diameter over the outer race. And the lowercase d is going to be the inside diameter on the bore or the inner race, right? Now, when I look over to the left, down the left-hand side is going to be the bearing number. Okay, that would be the part number that we would order. Next, you're going to notice that we have the bore or that lowercase d. So if we go up to the illustration, that's going to be the, if you would, the shaft diameter that we need to accommodate. And then capital D on the outside. And then C is going to be our width. And then we have a fillet radius. That's going to be on the inside right here. That will need to be taken into consideration when we do our shaft design, because when we actually shoulder it up, we have to have a radius that's small enough so that that won't get hung up. So we need to know that minimum radius. It's giving us the weight. And then at the very end, the last 2 columns, you're going to notice static load rating and dynamic load rating. Okay. Static load rating, dynamic. So the static is going to be our radial load, the one that is going to be the calculation from reactions at the supports. The extended dynamic load rating is going to be that C that we were calculating earlier. So if we go back to our spreadsheet, the 2 numbers that we're interested in are these 2 right here, 6,667 for our dynamic and then 650 for our radial. But they also threw in something a little bit more practical. They said, and you want to make sure that your bore is no smaller than 1.48, because what that's telling me is that's the minimum shaft diameter that we need to get in there. Okay. So, so if we go back to our spreadsheet here, number 1, we have to meet both the static and the dynamic load rating, and then we have to take into consideration the 1.48. So if we look over here on the right-hand side, and we look down the extended load rating, our load rating needs to be 6,667. So in the first kind of section here, you're going to notice that unfortunately we only go to 6,200. That's not big enough yet. So we're going to go down and we're going to look at the next one. This is the light series, and this one does approach in there, right? So we've got 6,950 would be okay. Then we're going to go back to the left one row, and I should say to you, you're going to notice that the black numbers are pounds and the red numbers here are newtons. You probably picked up on that already. Also, bearings are going to be sized to the closest millimeter. Okay, so if you look over here on the right, the newtons are coming out to even numbers and our pounds are off. Or I shouldn't say, they're just not to nice numbers. And if we go over even further to our diameters, whether it's the bore or the outside diameter, they're hitting on nominal millimeter numbers. And then our inches are going to be equivalent to that. Okay, which is fine. It's really not a big deal, but just so that you're aware. So going back over here, our dynamic load rating 6,950 would be something that would work for us. And then if we go to the left, we have to make sure that the static load rating is high enough, and it is. Most often that dynamic load rating is going to be the one that's going to dictate between the loads. And then what we need to do is we need to go along that row, and go all the way over to the left until we get to the bore. And you'll notice that the bore is 2.16. So 2.16, that's much larger. So what that means is in our design, we're just going to have to put more material on that board, because this number, our dynamic load rating, is dictating how large this has to be. If we would go down to 1.48, which would be 1.57, right, is the lowest. If we go over, we're not meeting the minimum dynamic load rating. Okay, so all three have to be satisfied. You have to have your minimum dynamic load rating, your static, and then also the shaft diameter. All right, so in this case, the dynamic load rating is dictating. So our shaft is just going to have to be bigger. So you might have to do some juggling around, if you would, in accommodating a larger bore bearing in order to get the life that we need. Okay, so now at this point, what we would do is we would say, all right, so if we're picking that bearing, it's not ideal, it's the second one down here. Our bearing number is going to be 9111K. So I'm going to go back to my, spreadsheet, my bearing vendor. Now, this particular vendor is Fafner, which has been probably bought out. Fafner, I think it's Torrington. I need a G in there. And then our part number is going to be the 9111K. And then you just have to tell me what page on there did it come from. So if we look, I think, I don't know if I have the official page number on here. I guess we would call it page 1 of our PDF. Dang it. I guess I might have cut that off. Okay, that's all right. Page 1. And then we want to know, what is the nominal bore size? So we're going to go over here. And we're going to find our 9111K, and our nominal bore size is the very first one here. And it's 2.1654, 2.1654. Oh, I gotta make that pink. I'll do that later. Static load rating. So we want to fill in what was the static load rating for this. So I'm going to go back over here. I've got to go all the way over here. It's going to be 3,800. Sorry, I thought I didn't update the, I added some of these fields, so I didn't update it to be pink. So make sure you do that, because it's going to look nicer. And then I need the dynamic load rating, which is 6,950. And then I need my shaft diameter limits. Now, if we look here, you're going to notice that it's giving us a tolerance on our bore. Okay, this is going to be the tolerance on our bore. This is not the tolerances that you're going to incorporate into your design. This is on the actual board, like the product, that these are the tolerances that are going to be on that board. This is not what we put into ours. What we need to do is we need to go to their engineering section, and we are now going to then find where this bearing is, and it's going to tell us what the actual tolerances are going to be. So if we go back to our Canvas Module 3 learning plan, the next two PDFs are what we're going to download. So one is for shaft fits and one is for the housing fits. Now, in this particular catalog, this is like in the back of the catalog. The catalog was about 1.5 inches thick, and this is what we call the engineering section. You're going to want to try to find something like that for whatever vendor you're looking at, okay? But again, rather than going through all the pages in a PDF online, I thought this would be easier. So now we're going to open that up. So I'm going to go to the bearing shaft fits chart, and notice that it's green. So it's a little bit different color. So this is the engineering section. This first section is just the shaft fits. It says shaft and housing fits because it's a section, but I just pulled out on this PDF just the shaft fits. Now what we're going to do, I need to zoom in here a little bit. We are going to find our basic bearing number, our basic bearing number. So we are in a 9100 series, and then our last two digits are 11. So we're right here. So this is going to be our row. So 9100 and then 11. So now we're going to go over to the right. The first section here is just what the bore tolerance is, and this is on the actual bearing. So this is not what we want yet. We're going to go to the next sections here. So the first portion, it says, it's kind of letting you, it's kind of asking you about your application. Do you have a shaft rotating and load stationary, or do you have a shaft stationary, load rotating? So sometimes the shaft is going to just sit in one spot and then something else is going to just rotate around it. Or you're going to have the shaft rotating and then the part is going to be stationary. Okay. So you get to decide. We weren't given that information. The most common is that the shaft is rotating. All right. And then over on the right-hand side, there's some other options as well. So most often it's here. So you can see that over here, it's going to be shaft stationary, load stationary, and then it's going to be shaft rotating, load rotating. So most often it's going to be this one for classic applications. Okay. Now, when we talk about, for instance, gears, the load would be stationary. Even though the gear is rotating, the point of engagement remains at that same spot. Does that make sense? That's where the load is being transmitted, and that doesn't move. All right, that's not rotating around. The teeth are rotating, but their engagement is at that same spot each and every time. So when we do our gears later on, this will be the same column that we use. So I come over from my 11, and now you're going to notice up at the top here, here's where they give us our shaft diameters. They tell us what is the maximum value, what is the minimum value. Eric. Yes. Yeah, because where the load is being transmitted remains in the same spot. Yeah. Yeah. Okay. So now it's telling us these are the limits that we would put where we are going to be mounting this bearing. So we want our shaft diameter to be a max of 2.1660 and a min of 2.166 or 1655. So I'm going to write that down because that's what we're going to fill in for our Excel spreadsheet. So these are the limits. So to write the limits, rather than having two different cells here, my idea was 2.1660 over, so the max first, 2.1655. And those are the limits, the high and the low limits for that. And then what page is that on? I hope I hope I didn't cut that off of this. Oopsie. Hope I didn't cut that off of this one. Let's see. There is only one page. Yeah, it's either 34 or 36. E34. Yep, down in the left-hand corner. Write that because truly you would be finding this in a catalog. E34. Now we're going to go to the housing diameter. Okay, housing diameter. So that outer race has to get pressed into a housing. So so we're going to go back over here, and this time we're going to look at the other download that we did, the bearing housing fits, and it's a very similar sheet, but this time it's housing fits on the side, on the top. So I'm going to zoom in one more time. Now this one we read a little different. This one we want to find our 9100 series. That's the extra light column going down here, and we want to find the actual number. So we want to find 9111. Now this is the basic number. You don't have to worry if the K is not in there. That's okay. That's like a little adder. I think it's a seal or something like that. And now we're going to go across this column, and you'll notice that I have them circled. Might have looked at this before. 3.5433 is going to be our max, and 3.5442 is going to be our min. So that's that same thing at the top here. Now here again, most often your housing is going to be stationary, and in this case our load is stationary as well, just like it was on the original. So down here, I'll zoom in again just in case. These are our two numbers along that line. And this is on page E36. So we're going to go back to Excel 35433 over, see, 3.5433 over 3.5442. And again, when you then design for where this is going to be pressed into a housing, that outer race, those are the numbers you specify on your drawing. And this is going to be page E36. And then I'm going to straighten this out. I'm so sorry. I thought I added some things, and I guess this was the last little detail, oopsie, that I did not account for. Oops. Oh, no, I didn't. Shoots. More colors. I got to set that one as current, and then now should be able to get it in there. And then I'm gonna put them all in the middle, right? Looks better if they're all in the middle. And then maybe even bold them, because those are our answers. Okay, so that would be finishing it out. So these are not ones that you're going to actually grab from the top, but now this is where you're going to pick the actual bearing and specify, you know, the vendor and the details, if you would. Okay. All right. Questions on that process and using the vendor catalog pages, individual pages? Okay.
Yeah, I got a question actually.
Yeah.
So when you did the housing diameter limits, I noticed that you picked your numbers from the housing stationary load stationary, like
Correct.
that first column.
Yeah.
I might have missed why, but could you explain
Right.
why we wouldn't follow?
Absolutely. Yes. So on the previous one, when we did the shaft rotating and the load stationary, and I'm thinking of an example like what we'll be using, not the too far future, is going to be, let's say, a gear that's going to be mounted on a shaft. So the gear, even though technically the gear is rotating around, the point of engagement is stationary, but the shaft would be rotating. Does that make sense?
Yeah, okay.
Yeah. So since the load was stationary in that case, then since it's the same application, now the load is going to continue to be stationary even on the housing.
Okay. All right. Sounds good.
Okay.
Thank you.
You're welcome. You're welcome. Okay. Any other questions? Thank you. All right. So these will be the charts that you'll use then for your assignment when you specify the bearings. And again, you're not going to be using these numbers or creating any drawings, but just to have them at the ready when you need to. And I want to go and I'm going to show you, for instance, on the gearbox drawings, the shaft drawings. We saw earlier for the bearings, okay, what those diameters would be. Whoopsie, those diameters would be. We noticed that they're really small tolerances. And this would be then this diameter on the shaft. This is exactly where we would put those limits that we just found. Okay. These aren't ones we're going to make up, because if we don't use the manufacturers, again, I can't emphasize it enough. We can't guarantee that it's going to perform the way that we're anticipating it's going to, that we're designing into this particular, element. So, so it's really important that you use their information, because if it's going to be compressed more, the more press we put in there, the more it's going to compress. Well, now everything's going to like tighten in on there, and it's not going to rotate as freely. The life isn't going to be as long, as you can expect. And if it's not enough, now you can have it, actually slipping and not being appropriate. So be real intentional whenever you're incorporating any vendor. Use their data, use their process, use their suggestions, because they are the experts. Okay. Oopsie, go back over here. I think I've got to go back to my PowerPoint presentation. I'll just have to catch myself up. I think it's, we're close to the end. We're close to the end. Okay. Manufacturer's data. We did 14.1, 14.2, 14.3. And then we looked at the manufacturing catalog specifying the tolerances for the shaft and for the housing. And then just making sure, and we specified this at the end of that example, 14.3, adding those to your design summary at the end. So now you are ready Number one, to complete those practice problems. So these 3 examples, the first 2 were hand calculations. This last one, you can do the screenshots with the design information at the bottom, and then that would be your practice problems for module number 3. And then now you're ready to get started on assignment number 3. Okay, so what I'm going to do is I'm going to stop our recording for just a second, and then we're going to come back and we're going to talk about the homework and how to approach that.